Okay, in the last lecture I finished at the point that critically mentioning that why porosity needs to be reduced in order to get better ceramics with higher flexural strength and modulus of elasticity. So just to refresh your memory, that if you have a very dense ceramic like which has more than 99% density, then you can get much higher flexural strength. Now this example has been given for alumina. At the same time, if you have more than 99% theoretical density, then you also can get larger elastic modulus. Now this is the trick to play that you can play while developing bioceramic materials for bone replacement applications. If the material has a very high elastic modulus and then you want to match the elastic modulus of that of the bone, then what you can do, you can get porous ceramic, so that you know that with increasing porosity the elastic modulus will be lower. Now you have to do experiments just to find out that what porosity level the material will have what elastic modulus. So if you want to get down to from 200 gigapascal to 70, 80 or 100 gigapascal, then you roughly know that around 40% or 50% for 40% porosity that you should have in the material, so that this material has the required porosity level. But remember, when the material is highly porous, then it has also consequently very low flexural strength. So it cannot be used for highly load bearing implant applications, or in other words, it cannot be used in biomedical applications which require large load bearing capability. Now this essentially tells you that like the way that strength and elastic modulus largely depends on the pore size. Similarly, K1C, I repeat, K1C stands for critical stress intensity factor under mode 1 loading. So critical stress intensity factor means, in last lecture I have mentioned that K1C you can define at Y sigma F root over pi A. What are the different terms here? Y actually a parameter which depends on the orientation of the crack with respect to the loading axis, as well as the nature of the loading, whether it is uniaxial loading or biaxial loading. In many cases, if the value of y is not given, the value of y is taken as 1 or 1.1. Now sigma f is the fracture strength, that means the stress value at which that particular ceramic fractures. A is the half crack length if this crack is in the volume crack, that means if crack is well within the ceramic body, or if the cracks exist on the ceramic surface, then the full crack length is taken as A. Now from this it is very clear to you that critical stress intensity factor under mode 1 loading does not depends not only on the stress value but also the crack length value, and that has been mentioned here that let us say for good steel, like the steel which has a very good mechanical properties. Now if K1C is, let us say 100, now K1C is a fixed value. So what it shows, that I think I will spend some time on this slide, that what it tells, that if the steel has a very good mechanical properties and the K1C is 100 MPa square root meter, then the value of A is that crack length that it can be tolerated for the same steel which has a fracture strength of 100 MPa is 320 millimeter. 320 millimeter this means it's very large crack length, and typically if the material has any size which is less than 320 mm, that means that material is safe. Okay. Now if you go to cast iron which has a 20 MPa square root meter fracture toughness, and the same strength value, if the cast iron has a strength value of 100 MPa, 100 megapascal, then the crack length is 13 millimeter, and 13 millimeter means that if any cast iron sample which has a length or which has a size more than 13 millimeter, then it can be, and if it contains a crack length of 13 millimeter, then it is dangerous. Now typical ceramic Now ceramic is, let's say, alumina, which is a bioceramic, and in case of alumina, if K1C value is 4 MPa square root meter and for sigma f is 100 MPa, then it can be only tolerate 510 micrometer. So 510 micrometer means it is much less than a millimeter. Okay. So if your sample size is of 3 millimeter or 4 millimeter or 10 millimeter size, and if the same sample has a K1C value 4 and the fracture strength of 100 MPa, then you can very well see from this table that only 510 micrometer crack length can be tolerated. Anything larger than 510, it will lead to unstable fracture propagation. Now extremely brittle ceramic, for example glass. Now many applications bioglasses are used, and the glasses that extremely brittle, they have a fracture toughness of 1 MPa square root meter, and then you can only tolerate up to 32 micrometer. So what you can see that there is an order of magnitude difference. You go from 320 millimeter to go to 32 micrometer. So 32 micron means 32 10 to the minus 6. 320 micrometer millimeter means 320 10 to the power minus 3. So in other words, 32 into 10 to the power minus 2, and then it goes to here 32 into 10 to the power minus 6. So what is the order of magnitude difference? Order of magnitude difference is 4 orders of magnitude difference. If you go from good steel, which is which is a fracture toughness of 100 MPa square root meter, and if you go to very brittle ceramic, which is a fracture toughness of only 1 MPa square root meter. So by decreasing the fracture toughness value by 2 orders of magnitude, the maximum crack length that can be tolerated in these materials, that can be reduced by 4 orders of magnitude. So I again emphasize this point. So 320 millimeter means 32 into 10 to the power minus 2 meter. 32 micrometer means 32 into 10 to the power minus 6 meter. So when you are decreasing the fracture toughness from 100 MPa square root meter to 1 MPa square root meter, that means you are decreasing by 2 orders of magnitude. By decreasing in the 2 orders of magnitude fracture toughness, the maximum crack length that can be tolerated in the material, that decreases from 32 10 to the minus 2 to 32 10 to the minus 6. That means 4 orders of magnitude difference. So that comes because of the square root dependence of the crack length. So that means that this crack length has much more significant influence on the fracture toughness value of the materials. Now if you go to the next row, if you increase the fracture strength from 100 MPa to 500 MPa, now what you notice here, that your tough metal like good steel, you have the maximum crack length that can be tolerated is 13 millimeter. And if you go to that brittle ceramic, there the maximum crack length that can be tolerated is 1.2 micrometer. Again 13 into 10 to the power minus 3, okay, and there you can get 1.2, that means it's 12 into 10 to the power, so 1.2 10 to the minus 7. So this is 12 into 10 to the power minus 7, that is the crack length in very brittle glass, and 13 10 to the minus 3, that is in very tough metal. So again there is a roughly like 4 orders of magnitude decrease in the maximum tolerable crack length. And only thing is that other thing that you notice, that if the fracture strength of the material can be increased to higher value, then maximum tolerable crack length for any given material is subsequently or systematically reduces from 320 mm to 13 mm. Okay. So the thing that I am trying to mention here, that by microstructural design you can always increase the fracture strength, but for brittle ceramic you can immediately see by increasing the fracture strength you have a opposing directions. That means increasing the fracture strength will be accompanied by a decrease in the length of the maximum tolerable crack length. Okay. So that means you can always increase in the strength of the materials, but then it should be accompanied by that the critical crack length that you can tolerate in this microstructure. So in that high strength materials, the maximum tolerable crack length is very fine crack. Okay. So very fine crack, if it is present, it can lead to fracture. So therefore, you can see 500 MPa when it is fracture strength, then this critical crack length is 1.2 micron. 1.2 micron is extremely small crack length. So any crack length which is greater than 1.2 can easily lead to the fracture of the entire ceramic. Is it clear? Then, so for basically for ceramic materials, you know, there's a fracture strength. So if sigma f that increases, your critical crack length, let's say AC, that decreases systematically, okay, at a given K1C value. So when K1C is constant, that if sigma f increases, your AC, that is the critical crack length, that significantly decreases, and this decrease is quite significant, as you have seen in the table. Other thing is that at a given sigma f values, that when fracture strength is constant, that if your K1C decreases, then your AC, that is the critical crack length, actually, sorry, if K1C increases 100 MPa square root meter to 1 MPa square root meter, so you are actually decreasing the fracture toughness. Now if K1C decreases, then your AC value decreases by more than 2 orders of magnitude. So what it means, that, you know, if K1C decreases by 2 orders of magnitude, then AC will decrease by 4 orders of magnitude. Okay. So basically, the whatever order of magnitude decrease in the K1C, your critical crack length value will decrease more than 2 times the same order of magnitude. So if the K1C decreases by 3 orders of magnitude, then that AC value will decrease by 6 orders of magnitude. So that is what so that is what we are trying to mention here. And then if you go back to the next slide, now what you see here, that there is a Griffith's crack theory. This is a famous crack theory of proposed by Griffith. Now what it in this Griffith crack theory, if you have a rectangular plate, and this rectangular plate has a central crack, okay, and this rectangular plate has a central crack. Crack means this is a dense solid, and this solid, their interatomic bonds are not extended across this crack face. So therefore there is a kind of void space here. Now you have the 2 edge here, one edge is here and one edge is here, and in the last lecture I have shown you that at the tip of the crack, your stress is, if you consider this volume element and this is sigma, so at the tip of the crack, this stress value is much higher than the stress value that you are actually applying, or in other words, there is a stress concentration at the tip of the crack, and this stress concentration value you can find out is by sigma tip is equal to 2 sigma A by rho to the power half. Now what is the value of A? A is the half crack length, because this is your 2A. So 2A is the total crack length, and what is rho? Rho is the radius of curvature at the crack tip, and this radius of curvature at the crack tip is important, and that indicates what I have mentioned in the last lecture, is that for a longer and sharper crack, the stress intensity factor increases. For longer and sharper crack, crack tip stress intensity significantly increases. So whenever the cracks are longer and cracks are sharper, that essentially indicates that your crack tip stress intensity also significantly increases. Now this is some of the important thing that you have to remember all the time, as far as you are dealing with ceramic based materials. Now other things, that there is a other theory called English R1 theory of brittle fracture. What it says that if 2c by rho into sigma f, that is the stress at the crack tip at fracture, if it is equal to E gamma by R naught, that is the theoretical cleavage stress. Now what it means by theoretical cleavage stress means, now remember from the basic physics of this fracture of these brittle solids, okay, from the basic physics of the fracture of brittle solids, now if this sigma tip is greater than interatomic bond strength, that means at this crack tip region, if the sigma tip values are greater than interatomic bond strength, interatomic bond means this there is a ionic bond or covalent bond in the material. Now if the sigma tip is greater than interatomic bond strength, then this crack will slowly propagate, leading to the fracture of the material. Okay, so that is the point I want to mention here. So therefore the same criteria has been used by English and R1, and what it says that sigma max at the crack tip at the point of fracture, so this fracture strength means this when sigma becomes sigma f. So when sigma becomes sigma f, or in other words, you are applying the external stress which is the value of the point of fracture, at that point 2c by rho into sigma f would be equal to sigma max, that is the maximum stress at the crack tip, and if that is equal to square root of E gamma by rho. What is E? E is the elastic modulus of the material. What is gamma? Gamma is the surface energy of the material, and R naught will come from your very fundamental interatomic energy potential well. So interatomic energy potential well means that is the interatomic force between two atoms, and as a function of the interatomic distance, if you plot, then it shows a kind of potential well like this, and the potential energy minimum, this value is known as the R naught value. Okay, so I repeat, what are the different terms? C is the crack length at the point of fracture of sigma f. Rho is the crack tip radius of curvature at that criticality condition. Sigma f is the externally applied stress, sigma is equal to sigma f. Sigma max, it is the crack tip stress intensity or the stress which is realized just at the crack tip. E is the elastic modulus of the material. Gamma is the surface energy of the material, and R naught comes from the interatomic energy potential, that is the interatomic force if you or interatomic potential energy U if you plot as a function of R. Now this R value, where it is the minimum of the U, that interatomic energy potential, that is the lowest interatomic potential energy, and that corresponding R value is called R naught. Now from that, so this is the equilibrium bond distance. So R naught is nothing but equilibrium bond distance, and if the crack is atomically sharp, then rho is taken as R naught, and from that you can find out that sigma f is equal to half of E gamma over C, and then E is the elastic modulus again, gamma is the surface energy, and C is the crack length. So this is the so essentially this particular plot shows you that how the stress and strain, they are perfectly linearly proportional to each other in case of the ceramic material. Now this is for the alumina. In case of alumina, it has a large, so the steeper the line is, the more is the elastic modulus, because elastic modulus comes from the slope of the stress strain curve. And if in case of your glass material, the slope is much less. In case of alumina, the slope is much higher. That means glass has a much lower elastic modulus compared to alumina. The other things, you know that this stress strain plot, this has been recorded during the 3-point bending configuration, and this 3-point bending configuration, all the ceramic materials, it shows extensively linearly elastic behavior up to the point of fracture. The other things that has to be mentioned here, that in the ceramic, this as you know that ceramics are brittle materials, so therefore ceramics are very much prone to fracture. Now the question is, what are the two different types of crack systems in these brittle solids? The first one is called radial median crack. Now plus signs essentially indicate when you are indenting the ceramic surface. Indenting means you are placing the indents and let the indent making the full contact over the flat surface. Minus sign indicates you are actually unloading the surface. That means you are releasing the load so that indent comes back to its original position. Okay. And as you grow from plus to plus, that means you are actually applying more and more amount of load to the indent so that it reaches the maximum load. What it means, suppose you are trying to apply 5 Newton load, so you start with 0 and slowly increases to 5 Newton. And minus sign means from 5 Newton you just cannot come back to 0 just automatically. It has to be stepwise, it goes to 0. Now during the loading process, this side, so during the loading process what you see that as the indents will come in contact with the material, there is a deformation zone. This black zone is essentially the deformation zone just beneath the indenter, and it is the cross sectional surface you take. So essentially if you take this as a material surface, you take as an indent, so you are looking at from these directions. So you are looking at this direction, that is the transverse directions. So you are indenting the material from the top, and then just beneath the indentation you have this kind of largely plastically deformed region. Okay. And then what you see that after at the complete loading, when the loading is complete, then you see a very stable radial median crack. Now while unloading, now remember this material, this indent is here very sharp indent. So all these things are essentially valid for sharp indenter. Sharp indenter means this is like Vickers indenter. Vickers is a pyramid type of shape, so Vickers is a sharp indenter. Now when during the unloading, at certain point you see that another type of crack which will start propagating from the other directions. So which direction it is? It will be at the 90 degree to that of the radial median crack. Okay. Now that will be generated and that will go through, and when it is completely unloaded, this lateral crack you will be completely touching the surface. Okay. Now what happens if you relate this kind of behavior to the actually the friction and wear scenario like tribological scenario. Now you can consider that it's a sharp indentation and multiple sharp indentation, they are going just like this. So once this lateral crack forms, they touch the surface, then this is the hatched region which can be taken off from the surface, or which can come out as the due to the spalling of the material. Now when this indent is coming at this point, indent to go like this and indent goes like this. So when it goes like this to and fro motion, then what will happen? This more number of spalling will occur, because these lateral cracks will come in contact with the material much extensively, and this lateral crack will lead to the fracture of the material. So in case of the sharp indent, you have the two types of crack. One is the radial median crack and one is the lateral crack. Which crack do we use for this fracture toughness measurements? For fracture toughness measurement, you are actually measuring these 2C values. Like in the Vickers indent, you are actually measuring these 2C values in this direction, and you are measuring also in those directions. Okay. And what is your 2A values? 2A values is just what is mentioned here, that is your total Vickers diagonal. Okay. So however, if you use the very blunt indenter, what is blunt indenter? Blunt indenter means like, you use this Brinell indenter. So this is the case that you get for the blunt indenter, and the example of the blunt indenter is the, let's say, Brinell indenter. Now this Brinell indenter, again this plus sign means it is a loading, and when you keep on loading, then slowly some pre-existing cracks will be activated, and these pre-existing cracks will further propagate. This plus means it is complete now, it is completed loading. And then you more and more you load the flat surface with this Brinell indenter or blunt indenter. So blunt indenter means, suppose you replace your Vickers indenter by spherical steel ball, and this spherical steel ball you indent it from the top surface. Then what will happen? These cone cracks. Why it is called cone cracks? because it will, when the cracks are fully developed, when it is fully unloaded, this indenter will go up and will not anymore in contact with the material, then it will actually form this kind of cone crack. Now these cone cracks has been seen or observed in the soda lime glass. And soda lime glass, why glass material has been used? Because glass material is transparent. You can see the cracking behavior in the glass material. Many of your ceramic materials, they are not transparent, right? So you cannot see how the cracks are generated at the subsurface region. And what you see here, this cone crack actually essentially formed here at this region, and this region it characteristically forms a geometrical cone, and this cone has a typical length is alpha is 22 degree. Now people have done experiments on soda lime glass, and this indentation tests were carried out in inert environment. Now why inert environment? Many times if you do this testing in this aqueous environment or any acid environment, then aqueous and acid can additionally lead to more chemical attack on these glass materials. And inert environment means, for example, this indentation tests are carried out in vacuum. Vacuum means there is no aqueous environment outside, so you can exclude the influence of that any external liquid environment on the glass materials. Now if you change the load, let's say you start with the 5 kilonewton, 10 kilonewton, go to the 15 kilonewton, and each case you correspondingly measure that what is the cone crack length. Okay, so this is your cone crack length, and if you plot this P versus this C to the power 3 by 2, now it forms a more or less like a straight line. So that means P is proportional to C to the power 3 by 2. Okay, so this indentation load is proportional to crack length to the power 3 by 2. It does not have a typical linear relationship like P is proportional to C, but P is proportional to C to the power 3 by 2. Now what you see here, in case of the radial crack, what you have seen, what is formed in this sharp indenter like a Vickers indenter. In case of the radial crack, even similarly, if you increase the load, indenter load, and if you increase the crack size, so by increasing so if P increases, your crack size also increases, right? That comes from your basic physics. Now if P increases, C increases, and again if you plot P versus C to the power 3 by 2, then again you are going to get a straight line. That means P is proportional to C to the power 3 by 2. And what is the C value? If you go back to this length, this is your C value, this is your C, because this is your total 2C, so half of the C is this one. Okay, so you measure the crack length and you measure the indent load, and systematically if you vary that, then if you plot it, then you get P proportional to C to the power 3 by 2. So what is the summary of the thing? In case of the blunt indenter, you get radial median crack as well as the lateral crack, and in case of the sharp indenter, you get radial median crack and lateral crack, and in case of blunt indenter you get a cone crack. In both the cases, irrespective of the crack geometry, you get P is proportional to C to the power 3 by 2, where P is the indentation load and C is the crack length. Now single edge V-notch beam technique, that has been also mentioned earlier, and then single edge V-notch beam technique. Now there are two ways you can find out this fracture toughness. There are two ways you can measure the fracture toughness. One is the short crack toughness measurements, and another one is the long crack toughness measurements. Okay. Now short crack toughness is typically measured by indentation, because the crack length is very small with respect to the long crack that you typically measure, and long crack fracture toughness measurement is single edge V-notch beam measurement. For example, Now this is the long crack toughness which is recognized as most reliable. Now then the question is that why short crack toughness is measured? The short crack toughness is measured because it is most easily obtainable and you can get it for in the laboratory scale experiments within very reasonable time frame. And then second thing is that when you are trying to develop a series of materials, and these materials they are developed by changing the composition or by changing the processing temperature, then each time you cannot make a ACVNB sample, because ACVNB sample making for ceramic material itself is time consuming matter, and therefore in order to avoid very rigorous measurements using ACVNB, the short crack toughness measurement is required. However, this indentation toughness you cannot use as a design parameter. It cannot be used as a design parameter. That what it means, like if you are getting an indentation toughness value, let us say for example 8 MPa square root meter, you cannot say the same material in actual real practice situations or in reality they will have the same level of toughness, because your short crack toughness is typically overestimates the fracture toughness. So therefore ACVNB toughness values are kind of realistic estimate. And all this information is valid only for brittle materials like ceramics. For metals you get a stress strain curve, and from this stress strain curve you can find out. For metals it is different issue. So you get a stress strain curve like this. So this is your stress and this is your strain, and then area under the entire curve is the measure of the toughness. But in ceramic you cannot get a elastic plastic kind of behavior in case of during this tensile stress strain behavior, and then for ceramics you have to adopt a alternative method to obtain the fracture toughness values. Now this is that. So in each case anyway you can give this, you can see that at one edge you have this notch, and then from the notch tip there is some cracks, and this if crack length, entire crack length is C here, then what you can do, you can put it under the two support rolls here in the 4-point loading configuration. From the two top roll you are actually pushing them by P by 2, and therefore this support roll must exert a load which is again P by 2. So this is like a from the equilibrium. Okay, coming back to the discussion on this long crack fracture toughness. So essentially single edge notch beam test specimen contains a notch as well as associated crack of length C, and this cracked surface, remember that when you put this in the 4-point loading 4-point bending configuration, and 4-point bending configuration, the loading side will be always under compression. So any volume element you take here, it will be under compression. The tension surface, it will be always under tension. Okay, so this is the opposite to the loading surface is always under tension. The loading surface is always under compression, and the tensile stress actually influences, or tensile stress actually enhances that crack propagation, or tensile stress triggers the crack propagation in the materials. So therefore if a crack is placed on the tensile surface, then this crack can lead to the fracture of the material very fast. Okay, so that is the reason in the single edge notch beam technique your crack needs to be placed on the tensile surface, and therefore the cracked surface needs to be placed opposite to the loading face. This is your loading face. Okay, so here you are actually loading it, and this is your compression phase, and then this is your tension phase, and in the tension phase you have to put the crack. Now depending on the geometry of the specimen, like what is the height, what is this one width, and what is this value of, this is the half of the span length in both the sides. So actually if your span length is L here, so this D is actually L by 4, this D is actually L by 4, and this will be L by 2. So L by 4 plus L by 4 plus L by 2 would be equal to L, and therefore, and then you can calculate the K1C value from this particular expression. Now toughening mechanisms. Toughening means the ceramics, as I mentioned a number of times, the ceramics are essentially brittle, they lack fracture toughness. So toughening mechanisms essentially indicates the mechanisms by which you can potentially increase the fracture toughness of the materials, okay, and these mechanisms are only applicable in the ceramic based materials, okay. And now let us go one by one. What is the different toughening mechanisms that they can possibly work in the ceramic based materials. Number one is the crack deflection. Now in the particulate reinforced ceramics, for example, this is your one particles, this is your a capital N number of particles. Let's say examples is that alumina, zirconia, particulate reinforced ceramics, okay, composites. So here zirconia, for example, say second phase, and you have a crack here. Now this crack will tend to propagate, but then since there are a number of particles are on its path, now how these cracks will propagate? Cracks will go, they will be deflected around the particles, and they will go like that, okay. So this deflection of the cracks, what it will have effect, that will increase the tortuosity. So so crack deflection essentially increases crack path tortuosity, and thereby crack tip driving force is reduced, and crack propagation can be controlled. So if you go back to the slide now here, then you will understand that when there is a particulate reinforced composite, now this crack will always, so crack tip is always associated with some stress intensity, because as you know that this at the crack tip, the total stress that will be experienced is much larger than the externally applied stress, okay. Now therefore the cracks will find its easy way if they propagate along this direction. However, since there is number of particles which are present on this on its crack path, this crack path will tend to be deflected by the number of particle boundaries, and if a crack path will go through this number of particle boundaries, then crack path tortuosity means it is a deviation from the straight line propagation. Highly tortuous crack path means it will go through like sinusoidal type of things, or it will go through like this. So if the crack path tortuosity increases, then what will happen? That total driving force that is available for the crack propagation, that is reduced, and if that is reduced, then the fracture toughness will increase, okay. Then second thing is that phase transformation. Now this is an unique property of the phase transformation. Now how this phase transformation can be improved? Like in case of the zirconia case, now in case of zirconia, there is a transformation which is known as tetragonal zirconia to monoclinic zirconia transformation. Now if there is a crack tip here, now if there is tetragonal zirconia which is present in this crack tip, and then what will happen? This tetragonal zirconia will be transformed in this crack tip stress field from tetragonal to monoclinic zirconia, and this kind of phase transformation is associated with the volume change of 4%. Now, if there is a volume expansion, then what will happen? This at the crack tip, these hashed particles are the monoclinic zirconia. Now, if monoclinic zirconia, because of this phase transfer, some volume will expand, but this monoclinic zirconia is also enclosed by a number of tetragonal zirconia. So, the neighboring particles will not like that monoclinic zirconia will itself try to increase in size. So, there will be some constraint effect, okay, and because of this constraint effect, there will be some compressive stress which will be acting on the crack tip. I will explain it what I mean by that. This in the case of zirconia, this tetragonal zirconia can be transformed to monoclinic zirconia in the crack tip stress field. So, this is your crack tip and there is an extensive stress or intense stress which is surrounded by the crack tip. Now, in this crack tip stress field, tetragonal zirconia will be transformed to monoclinic zirconia, and which is shown here in the case of these hatched circles. Okay. Now, once this transformation is completed, now there is a 4% volume expansion. So, now you think it physically, like these hatched circles are surrounded by all tetragonal zirconia, and hatched circles have a larger volume. So, therefore, hatched circles will try to expand because it has a larger volume, and if it tries to expand, the neighboring particles will not like that hatched circles will try to expand. So, neighboring particles will try to squeeze them, and that squeezing action leads to the compressive stress on the crack tip, and this compressive stress, if it is acting on the crack tip, then that leads to the closure of the crack tip. So, if there is any crack like this and there is a compressive stress is acting on both the sides, then what will happen? These crack tips will be closed. So, this crack tip cannot go further, and therefore, fracture toughness is improved. So, fracture toughness means it is a measure of the crack propagation ability in the material. If the crack propagation ability is reduced, then your fracture toughness is increased. Okay. Coming to the third mechanisms, which is known as the microcracking. So, which is known as the microcracking. Now, how this microcracking they can improve the fracture toughness of these materials. Now, if you come to this place, this is a crack here. This is a primary crack, or what we call as a major crack, and this is your micro cracks. I am writing mu c. Mu c stands for micro cracks here. Now, what it tells you that depending on your processing conditions, depending on your machining that you are taking the material prior to the fracture. Now, as we have seen that for the strength measurement, you need to take a bar specimen, and that bar specimen has to be cut from a larger specimens. Okay. So, then you are cutting by diamond saw. So, depending on the severity of your machining processes, all your materials are bound to have some smaller or final size cracks, okay, in the material. Now, this is your primary crack, and your primary crack has a much larger length compared to micro crack, that you realize first. So, as far as the length scale is concerned, your primary crack has a much larger length compared to your micro crack. Now, you know that your sigma tip, that is the stress that is concentrated at the crack tip, that sigma tip is directly proportional to the square root of the crack size. So, therefore, at the primary crack, your stress concentration will be much more. Okay. And then when this primary crack will have tried to propagate, then your micro crack, what it will do? The stress will be transferred to the micro crack, and in this stress tip region or in this crack tip stress field, micro cracks also will try to propagate. And if micro cracks will try to propagate, then what will happen? Lot of energy will be consumed from the crack tip stress field in the propagation of the micro cracks, and if the micro cracks will propagate, then the primary crack growth also will be reduced, because there is not much energy that will be available for the propagation of the primary crack tip. I repeat this micro cracking mechanism. So, essentially micro cracking mechanism based on the hypothesis that you already have pre-existing micro cracks in the sample. Pre-existing micro cracks means, as I said, micro cracks from the basic nomenclature you can immediately find, you can immediately realize that micro cracks means it has a length scale of micron size, let us say 2 micron, 3 micron, 5 micron, like that length scale. whereas primary cracks may have size of several microns, like 40, 50 or 100 micron crack length. Okay. Now, if these cracks, primary crack tip stress field, the micro cracks are present, then what will happen? Primary crack tip stress field has a much larger stress intensity because it has a much larger crack length, right? And if it has a much larger crack length, then this stress field, in this stress field, whatever micro cracks are present, these micro cracks will try to propagate faster because they will consume the energy from this primary crack tip stress field, and as a result, if the micro cracks will now grow in length, so that 2 micron length becomes 10 micron, then the total amount of stress field or total amount of energy that will remain at the primary crack tip stress field will be reduced, because some amount of energy is spent in making the micro cracks grow in length. Okay. And as a result, what will happen? The total amount of energy will be reduced at the primary crack tip stress field, and if the total amount of energy is reduced, then primary cracks cannot propagate the way primary cracks would otherwise propagate in the absence of micro cracks. So therefore, micro crack toughening means that propagation of the micro cracks in the crack tip stress field of the primary cracks leads to major toughening properties, major toughening of the brittle ceramics. Now, all these factors actually are much more relevant to your biomaterials also. Now, coming to the other aspects, that is the bridging zone, whisker reinforcement, the ductile metal bridging. This is somewhat important for your biomaterials, but not this one and not this one. I will explain to you what it is, and then subsequently I will explain to you why it is not relevant for biomaterials. Now, whisker reinforcement. Now, the next thing is the fiber reinforcement. Fiber means it is a long fibers which has a larger aspect ratio. Aspect ratio means here this length to diameter ratio is much higher. Particulate means it is a smaller aspect ratio, smallest aspect ratio. Particulate means mostly it is, spherical size, means in all the dimension it is RRR. So particulate, they do not have any aspect ratio. Now, fibers have a large aspect ratio. Now, if a crack will try to come and try to propagate through these fibers, now what will happen? These cracks cannot propagate to the other side of the fiber unless it breaks the fiber and go to the other side. You understand? So there is a physical obstacle. Each fiber will provide physical obstacle to the propagating cracks. So how it happens? So crack comes, then it breaks, then this interface of the fiber and matrix, there the cracks will propagate. Now suppose a crack is there at the fiber, and according to this crack it is activated in the crack tip stress field, and then cracks can go to the other side. Again it will be coming naturally to its own way, and it will try to propagate. Then what I am trying to mention here, each time a primary crack will interact with a fiber, then each time this crack opening displacement, that is called COD, this crack opening displacement is subsequently getting reduced. Okay. And finally, after interacting with, let's say, small n number of fibers, then crack tip is completely closed. Closed means it cannot propagate any further. So that is the way these fibers will lead to the toughening mechanisms. I repeat, when a primary crack will come and interact with the fiber, the primary crack will see the fiber as a kind of physical obstacle to its propagation. So the crack will not propagate to the other side of that crack. We cannot propagate through the fibers unless until crack will make the fracture of the fibers. And how this fracture takes place? Now at the crack tip fiber matrix interface, that your interface is brittle, and if there are some cracks on the fibers, then cracks will go to the other side of the fibers, and then they will delaminate the fiber matrix interface, and then they will propagate further. In each time crack interacts with the fiber, crack opening displacement significantly reduces, and unless until it is completely closed, that means cracks will not propagate any further, and that is the point that the major toughening is achieved. Coming to the whisker reinforcement. Now you know the fibers has a very long aspect ratio, and this is the case that we are talking about unidirectional fibers. Unidirectional fibers means the fibers is only oriented in one direction, not in multiple directions. Okay. Now coming to the whiskers, whiskers means when the aspect ratio of fiber is reduced. Okay. Now you can consider whiskers as a chopped fibers. Like, you know, if you have a fibers here and then you can chop it, that fibers, let's say 2 or 3 whiskers, then these whiskers have a much lower aspect ratio, right? So that you can clearly see from the slide. And these whiskers, if it is oriented this way, then others are oriented this way, others oriented this way. So in all these directions the whiskers are oriented. Okay. And this whisker orientation, like the fibers, that whiskers also lead to the crack bridging. Bridging means what? The two surfaces will try to come together and they will form a bridge. So similarly, that crack bridging also will be activated in case of the whisker reinforcement. However, from these two process description, you can immediately see that in case of the fibers, your toughening will be more compared to your whiskers, because in the whiskers case, your aspect ratio is reduced, and therefore the obstacles or the hindrance to the crack path propagation that it provides, that is also much less. Next one, now the question is that why these fibers and whiskers cannot be used in the biomedical applications. The answer is, now if there is a ceramic matrix and there are fibers or whiskers, then what will happen during in vivo applications? If the whiskers they released in the in vivo application because of the wear or fracture or whatever it is, then what will happen? That whiskers, because of the small length scale, they can be transported in the other part of the material, and they can cause the potential genotoxicity property, they can cause the potential inflammation in the materials and so on. So whiskers and fibers, they are never used, or they are never kind of what I would say approved or as such for the different federal agencies for the application in the biomedical applications, because of the potential risk that is involved in releasing these whiskers or fibers under the in vivo conditions. Okay. The last point is the ductile metal bridging. Now ductile metal bridging essentially tells you that you have a metallic particles. Now you know at the crack tip stress field, these metallic particles actually will undergo plastic deformation. Okay. Now this plastic deformation means they will essentially flow. Flow means there is a plastic flow of the ductile metals, and if there is a plastic flow in this ductile metal, then what will happen? With this plastic flow, this crack tip will be subsequently reduced, and accordingly this ductile metal will act more like a bridging. Ductile metal acts as more like a bridging element. So more the stress field, more the elongation or more the plastic flow, and ultimately this will be completely closed by a ductile metal. Examples of this ductile metal is, let's say, hydroxyapatite silver. Silver is a metal, hydroxyapatite is a ceramic. So the addition of the silver essentially is stimulated by the fact that in the crack tip in the hydroxyapatite, silver particles will undergo plastic deformation, they will flow and they will take part in the ductile metal bridging. Another example is that why hydroxyapatite titanium material is developed, because titanium is a metal, hydroxyapatite is a ceramic. So what was the postulate? Postulate is that titanium will undergo deformation, and that deformation will act more like a ductile metal bridging, and that will decrease the crack tip displacement, and as a result your toughness will increase. Okay. Now this is like more examples that you know that more kind of schematic diagrams as how different mechanisms they operate. Let's start with the transformation zone here. Now in case of this transformation zone, what you see that your zirconia case, that your in the process zone here in the dotted zone, your tetragonal zirconia transforms to monoclinic zirconia. That increases the volume expansion, and that is indicated by this, and then it experiences the compressive stress field, and that leads to the toughness of these materials. Micro crack, I have already told you the classical example is the alumina zirconia particulate reinforced composite. You have this alumina matrix or alumina particles as well as zirconia particles, and these micro cracks at the particle grain boundary that causes the cracks to be stopped at certain point. Then you have the ductile metal bridging, that you know in the tensile force here these metals will flow, and however once these metals will start flow, then they will kind of close the crack tip. You have the whiskers, these are the whiskers you can see. Now these small whiskers, if they are released under in vivo conditions, they really have potential health risk. Okay, so that is the reason whisker reinforced composites are not used. And typically the ceramics, traditionally ceramics, structural ceramics are also classified as monolithics and composite materials. Now monoliths means this is alumina, zirconia, silicates, silicon nitride, silicon carbide and sialones. Okay, and composite means this is a particulate reinforced composites, whisker reinforced composites and fiber reinforced composites. Okay. Now monolithics means that is simple monolithic ceramic without any second phase reinforcement, and monolithic ceramics are essentially extremely brittle. Catastrophic failure means that stress strain curve, if you plot, it goes and straight to failure. There is no deformation here. Particulate, whisker, fiber composites, the way it is goes that L by D ratio increases this way. Now if you go from whiskers to fibers, your aspect ratio increases and you have more and more toughness. And what you see here, that if you go more from the silicon carbide or metallic dispersions particulate reinforced, you can have silicon carbide fibers in silicon nitride composites, and you can have silicon carbide fibers or silicon carbide whiskers in silicon nitride composites. You can have silicon carbide fibers in silicon nitride composites. So these are like examples of the particulate fibers or whisker reinforced composites. The more you go to the right, more toughness you can achieve in the fibers and whiskers. But however, for biomedical application, as I said, these fibers and whiskers are not generally are to be avoided. Therefore, you are already left with the particulate reinforced composites, that is that you can have metallic dispersions in a ceramic matrix. Okay. And if your material is more tough, or if your material has a much higher toughness compared to that of the monolithic ceramics, then what will happen? This material also will have better damage tolerance property or better damage resistance property. So that is what has been meant by brittleness to catastrophic or damage tolerant property. Now this view graph tells you that how these whiskers will lead to the crack bridging. Now this is your whiskers, if you can see closely. Now these whiskers, this is your crack, this is your primary crack tip. And what you notice here, that in this primary crack tip, these whiskers are going and these whiskers are getting pulled out. Pulling means the whiskers are broken and whiskers are getting pulled in the ceramic matrix, and that leads to the toughness of these materials. So I think I'll stop here, and in the next one we'll start with that other important topics of biomaterials.